Okay, and we're back. We've kind of hit all the history. Now we'll start digging into some of the technicals of fiber optic. Um, I'm going to remind you of a couple things we talked about earlier that we should remember, but this will kind of get you back up to speed. I'm going to frame this in where are we typically going to find fiber optic in networks. Fiber optic is typically used for your WAN connections between facilities, but if I'm talking LAN in my building, where I'm typically going to find it is in my backbone wiring. Up until now, we've been talking everything copper patch cables to the outlet on the wall, copper horizontal cabling, copper patch cables in from the patch panel to the switch. So in my LAN, in my building, where am I probably going to find fiber optic? It's probably going to be the backbone connection, and that is the connections between my closets. It's not very common for horizontal wiring, but for backbone wiring, I would find it. Now, it is acceptable for use in my LAN for horizontal if I want, or backbone. I can use it for either one, but I'm typically going to find it as backbone cabling in my building, between my closets, if you will. Advantages, if you remember, it doesn't generate, it's not susceptible to electromagnetic interference, so any kind of magnetic fields around power wires, motors, that sort of thing, does not affect the data on a fiber optic cable. It has extreme high bandwidth compared to copper, and they can travel with very far with little or no attenuation. That's one of the reasons we do find it between closets and as WAN connections. It's non-conductive fiber because it's made of glass. Is good for grounding and bonding. So I don't have issues connecting my closets. I don't have an issue of, let me say that again. When I connect my closets together with fiber, I don't have an issue of a short, electrical short in one closet traveling across that backbone link to another closet. If I use copper between my closets, that can happen. An electrical short in one could travel across my copper cable to the other closet. It could do that. But being that I'm using fiber optic, it's non-conductive, that won't happen. This is also useful as I'm dealing with connections coming into a building. Lightning and those kinds of issues outside won't come into my building across fiber optic. It's not conductive. Disadvantages, it's obviously more expensive than twisted pair. Typically twice the cost of. And it kind of snowballs because, you know, the cable itself is twice expensive. The connectors can be $5, $10 a piece, depending on what they are. The tools, I need a whole new set of tools to deal with them, another set of testers to deal with it. So it really does snowball in cost. It is more expensive. It requires more expensive outlet configurations, yes. All the Jackson connections and everything, yes. I can't transmit power across it. Think about power over Ethernet. Power over Ethernet for copper cables out to an access point or phone. I can't do that over fiber optic. It is more difficult and time consuming to terminate, absolutely. It's difficult to test, yes. I need a special tester to test it. So, yeah, those are some significant disadvantages. So that brings us to the question, we mentioned this quite a long time ago, but when do I need or when should I use fiber instead of copper? Here's 4 good reasons. If I'm dealing with a high noise area, EMI, RFI, radio frequency interference, electromagnetic interference, if I have high noise areas, maybe an industrial application, I would probably use fiber optic. Cable runs beyond 100 meters. Copper can go 100 meters, but anything beyond that, I need fiber for that. So again, backbone connections between closets, perfect use for. Cable runs between floors and closets. As we said, it's doing electrical isolation. I won't have an electrical short go from one closet to another across the fiber link. It's non-conductive. High security areas, some military facilities use a lot of fiber optic because it's very tough to tap into. Think of it almost as a water pipe. If I drill into a water pipe, you're going to know it. You know, you're standing in the shower and somebody drills in the water pipe, the water in the shower is going to diminish. You're going to know somebody tapped into that water pipe. Same kind of idea happens with fiber optic. So high security areas, fiber optic often gets used. Going back to our construction, we have, it's made of glass, and I have the core cladding, strength fibers, jacket insulation kind of thing. I think I have a picture of that on the next page here. We'll get to that in just a second, just to kind of remind you, but that's our general construction. Plastic fiber is out there, but it's not blessed by LAN standards. Glass is the one that is preferred and used. Think of these as light pipes. Yes. Think of fiber optic almost as a light pipe, as you saw with the demos that I had done already. It's almost a light pipe. The fiber connections we're going to typically deal with are 2 strands, one for send, one for receive. And here's examples of SC connections, 2 strands, send, receive. Here's ST, send, receive. Yes, very common. Here's the actual construction of the fiber if I cut it away. We showed you examples this earlier semester, but starting on the outside, if I cut my cable jacket away, I find underneath it the strength fibers. Those with the yellow fibers, typically Kevlar, that are there for strength to try to keep this fiber from snapping as I'm pulling it or installing it in place. Under that, I actually have the glass stub, and then the glass stub is actually made of 2 pieces, the core and the cladding. As we said before, Corning Glass, they figured out how to make this using a gas. We'll get to that in a little bit. That way they can control the clarity, the indices of refraction of the core and cladding. But that's your basic construction of the fiber. And this glass stub that's out here is about the size of a human hair. So this glass stub that we looked at before is about the size of a human hair. It does come in 2 styles, tight buffer, loose buffer. Tight is the insulation itself is kind of adhered to the fiber. I would actually need to cut and strip that off. Or loose buffer, if you remember the Singlemode that we looked at and passed around. The Singlemode, it kind of reminds you of just a glass strand that is loosely in a tube. So your tight buffer, the insulation is adhered to the fiber. Loose buffer, these fiber strands are just kind of loose in a tube. Almost like, you know, a coffee stirrer inside of a larger straw kind of thing. It's just loose in there. 2 main types of multimode, Singlemode. Well, multimode is the one we're going to commonly encounter, especially in land environments. Multimode, I'm going to transfer data using multiple light rays. Multimode, multi-light rays. That's the term. And actually the picture down here is trying to show you the LED is emitting multiple light rays. And those multiple light rays are bouncing down the fiber, indicating a 1, a pulse of 1. When I send a pulse of 1, it emits a pulse of light, and that pulse of light is made up of multiple rays of light, multiple modes of light. So this whole thing here is a pulse indicating a 1, followed by no pulse of light, which would be a 0. Okay? So there's your multimode made up of multiple rays. The core diameter is around 50 to 62.5 microns. So it's a rather large core to handle the LED light source. Our cable lengths are usually in the few hundred meters up to about 500 meters, not very long. So again, good for in my building, in my building connecting my data closets together. Typical light source for this is LED, relatively inexpensive light source to send a pulse of light down the fiber. So this would be probably the most of the fiber we're going to encounter in networks and LANs is going to be multimode. Meanwhile, there is also Singlemode. Singlemode you're typically going to find in WAN connections or connecting buildings together. Think of connecting, if you've been over to Wildwood, you know, the Blocker building at Wildwood the whole way up to North Hall where they have the fire tower. That, because it's longer than 500 meters, would need to be a Singlemode fiber, Singlemode type of fiber to connect those 2 buildings. So I'm going to transfer data through a core using a single light ray, Singlemode, single light ray. So in this case, we're using a laser light source. You know, even your generic laser pointer is a focused beam of light. That laser light source is going to be aimed into the fiber, into the core. I can do a little bit more of a direct bullseye with a laser light source, if you will. And the core on this one is going to be much smaller. The cores are only around 8 to 10 microns, very small. So you're talking comparing a very large straw down to a very tiny coffee stirrer for core sizes. So there's my core. I have a very focused beam of light out of a laser into my core of my fiber. And again, this is 1 ray of light going down through, representing a pulse of 1, or a pulse of light representing a 1, followed by no pulse representing a 0. This is going to support large amounts of data going great distances. We can do tens of kilometers on this one. Typically for WAN use, and again, my typical light source for this is laser. More expensive light source emitting a focused beam of light into the Singlemode to be able to go longer distances. So typically LANs I'm going to find multimode. Typically WANs I'm going to find Singlemode. That's kind of generalizing, but it'll kind of get you sorted out on where you find them. And here's just another quick summary of those 2. Multimode LED light source, I'm typically going to have wavelength light sources in the 850 nanometers to 1300 nanometer light source. And I do have 2 different types of multimode, graded and step, graded or step refractive index used. And I will show you that in another picture here in a second. Meanwhile, Singlemode, I'm using a laser light source, a single ray of light down the core of the fiber, and my light sources are usually in the 1310 nanometers up to 1550 nanometers. Longer wavelengths to go, longer distances. Longer wavelengths to go, longer distances. So here's a picture of Singlemode, very small core, one single light ray, my laser light source going down the axis of the fiber, the core of the fiber. Single light ray, very small core, long distances for Singlemode. Meanwhile, I do have two different types of multimode. Here is my graded index. This is my 50-125, 50 micron diameter core, 125 diameter cladding. This one, the index of refraction from the core to the cladding is gradual. It's not quite so distinct step between the two, and because of that, as the light goes to leave the core, it's bent, it's coerced, it's coaxed back into the core of the fiber. So my light ray is very gently coaxed down the fiber. Meanwhile, my step index, which is your 62.5 125 fiber, 62.5 micron core, 125 micron cladding. This one, a little bit larger core, and there is a very distinct difference between the core and the cladding indices of refraction. And because of that, when the light ray hits it, it's going to reflect. It's going to bounce off, if you will. It's going to reflect, almost like a mirror. So the light rays are kind of like forced down the fiber. Bounce, 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 bounce. So it's not quite as gentle on the light source. So what you end up finding when you do a little bit more reading is your multimode step index, 62.5, the light signal does not go as far because it's not treated as nicely, if you will, as the graded index. The graded index can go greater distance because it's very gently coaxed down the fiber. And here's the summary of those sizes I was just mentioning to you. Multimode 50-125 is your graded, 62.5-125 is your step index. And your single modes are typically in the 8-125 or 10-125 diameters. And here's just quick kind of a graphic trying to show you the step index. Here's your core to cladding. Here's the grade index core to cladding, just a little smaller. And then your single mode, very small core to cladding. And as you can see, LED light sources for multimode, laser light source for hitting a bullseye on this core. Then here's just a quick reminder on the size of things. We're not used to dealing with microns, but a 62.5 micron core is about 2 to 3 thousandths of an inch. Meanwhile, the cladding of 125 is about 4 to 5 thousandths of an inch. Just to put it in perspective, human hair is in the up to maybe 7 thousandths of an inch. Piece of paper is usually, paper that you'd have a copy paper out of your printer is usually around 4 thousandths of an inch. So the cladding of the fiber is about as thick as a piece of paper, and I'm trying to hit a bullseye on the middle of that. That's why you're using your laser light source for a lot of these. And there's just kind of showing you a relationship magnification of the sizes of your microns and everything else, just to see if you can put it in perspective. All right. I'm going to stop there. When I come back on the next one, we'll start talking about how fiber optic is actually made.